Hello and welcome back to part 2 of lecture 31. In the previous part we introduced what an adjoint operator was, and I thought I would do an example first of all just so you can kind of see what's going on here. Okay, so here, let's clean this up. So we have a linear transformation going from R2 to R3, and it's defined by taking the pair x1, x2, and it maps it to 3x1, 4x2, 6 times x1 plus 7 times x2. And what we need to do is we need to find the adjoint, which according to the definition is a map that goes from R3 to R2. And just to remember, what we're doing here is we need an inner product on R2 and the inner product on R3. And we're just going to use the standard inner product, Euclidean inner product on both of these spaces. Okay, so here, let's try to write a little neater here for you. Okay, so first of all, let's just think about what we have, right? So on the left-hand side, right, this is equal to the TV, comma, the W, okay? And that what we have to figure out is what the T star is. So first of all, this is inside of W, and let's replace the Tx1, x2 with what it's equal to, right? So this is the inner product of 3x1, comma, oops, let me try that again. This is equal to the triple 3x1, 4x2, 6x1 plus 7x2, and you're doing the inner product with y1, y2, and y3. Okay, so now we're doing this is the inner product in R3, right? So this is the inner product in R3. So we do the normal inner product. So this is equal to 3x1 times y1 plus 4x2 times y2 plus 6x1 times 7x2 times y2. And now notice that there's a different way of regrouping it. We can put all the x1s together. So we would have 3y1 plus 6y2 times x1. And then we put all the x2s together. So we would have the rest of it, I guess, 4y2 plus 7. Oh, sorry, this should be a 3 right here. That's a 3 plus 7y3. And this gives me, hopefully I did everything right. This should have been a 3 as well. I apologize about that. That's a 3. So this is x2. So I've kind of regrouped it here. So here it's like something times y1 plus something times y2 plus something times y3. But instead I'm going to write it as something times x1 plus something times x2. And notice that the way that I've written this is that this is the inner product of the pair x1, x2, comma, 3y1 plus 6y3, comma, 4y2 plus 7y3, right? So this is the inner product in R2, right? So this is how we go from here to here. And so notice that this is going to be equal to our vector x and t star of w. Okay, so one way to summarize what we have is that this implies that t star takes the triple y1, y2, y3, and it sends it to the pair 3y1 plus 6y3, comma, 4y2 plus 7y3. So that's how I now take a triple of elements and I send it to something in R2. Okay. Now, some observations which are going to kind of drive what we're going to talk about in the rest of the lecture is, first of all, we notice that this new map that we have here is actually a linear map, right? It's actually a linear map from R3 to R2. And probably the more interesting observation is that the matrix associated to this linear transformation is 3, 0, 6, and 0, 4, 7, right? Because the first basis element gets sent to 3, 0, 6, and the second basis element gets sent to 0, 4, 7, right? So that gives me that first column. But now, if you do the same thing, this is a linear map, and you say, well, what is it sent to? Okay, this is sent to 3, 0, 0, 4, 6, 7. And if you remember anything from Math 1B03, you notice that what we're getting here is the transpose of the matrix that we started with. Okay, so this is kind of going to be a very useful observation. We're actually going to explain kind of why this is the case later on. And also to justify why the first statement is important is because when you look at the definition, it just says you're defining a function from W to V. It doesn't actually say that the function that you found is actually a linear map. So is this particular example, is this just kind of a one-off, or is this something happening in general? And in fact, it turns out that this is something that happens all the time. Namely, if you start with a linear map, then the adjoint, and I wrote this actually wrong, then the adjoint is a linear map going from the vector space W to the vector space V. Okay, and let me show you how the proof goes, because it's a good example of how these proofs work, okay, some of the properties, okay. So you need to show, right, that T star of W1 plus W2 is the same thing as T star evaluated at W1 plus T star evaluated at W2, and we have the scalar property for our linear map. Okay, so let's take a linear map from V to W, and let's take two elements, W1, W2 in W. So if V is any element in our vector space, we know that V with the adjoint of T of W1 plus W1 plus W2, well, this is equal to TV W1 plus W2, right? This is actually the definition of the adjoint. Right, so the definition of the adjoint, and this is a useful trick. So it's a useful trick, right? We swap order, so replace T star with, we replace the T star with a T, and usually that's something that we're given for. Okay. Okay, so now we get this. This is now using the inner product in W, and by the properties of inner products, we know that this is equal to TV W1 plus TV W2. This is properties of linear operators. And now we use the definition of the adjoint again. This is the same as V T star W1 plus V T star W2. And then we can join these back up, right? So this is equal to V comma T star W1 plus T star W2. So all of these steps right here that I just did are just kind of following from the properties of linear operators. Okay. Now, by the Riesz representation theorem, T star W1 plus W2 is unique, right? This is the unique element that allows us to go from one side to the other side. But we also have V T star W1 plus T star plus W2 is equal to the same thing, right? So that means that this term and this term actually have to be the same element because it's unique, right? So we have to have that the adjoint of T evaluated at W1, W2 is the same thing as the adjoint evaluated at W1 plus the adjoint evaluated at W2. Okay, so that's how we use the Riesz representation term. And the proof for the scalar multiplication is the same. It kind of has the same sort of shape. We take a linear operator, we take a W in our vector space and our scalar, and then the inner product of V and the adjoint of T of the W scaled by lambda. Well, we can use the definition of our linear operator, right? So this is equal to or not our linear, our definition of adjoint. This is the same thing as TV lambda W. Now we can pull out the lambda, but because it's in the second spot, we have to take the conjugate. So we get TV W. Now using the definition of the adjoint again, we can put this into the order V, adjoint of T W. And then we can pull in back in the lambda again, so we get V lambda T star W. And now this, by definition, this is the unique term that gets sent, that it gets associated with this inner product. But we also see that this guy gets sent to this. So by the Riesz representation theorem, okay, so by the Riesz representation theorem, that these two things have to be equal. Okay, and so as a conclusion, we know that the adjoint is actually an example of a linear map. So when we come back after the break, we're going to introduce some properties of the adjoint, and I'm going to kind of bring in this idea of the transpose of the matrix.